before we finish with our discussion of dispersion IFAs and dipole-dipole IFAs, let's make a direct comparison between the effects of dispersion and dipole-dipole IFAs on a physical property such as boiling point of molecules. Because dipole-dipole IFAs are stronger than dispersion IFAs, and this is a direct result of polar molecules being permanent dipoles rather than just instantaneous or temporary dipoles that we were looking at a moment ago with dispersion IFAs. Because dipole-dipole IFAs are stronger than dispersion IFAs, polar molecules will have higher melting points and boiling points than nonpolar molecules of similar molar mass. And it's important to make sure that when we do a comparison, we're looking at molecules of similar molar masses so that the strengths of the dispersion IFAs will be about the same in both. Remember that dispersion IFAs will increase with increasing molar mass. So if we truly want to see the effect of the strength of dipole-dipole IFAs on the difference in boiling points of molecules, we need to look at molecules of similar molar mass so that their dispersion IFAs are about the same and will cancel out in the comparison. So polar molecules will have greater melting points and boiling points than nonpolar molecules of similar molar mass, reflecting greater attractive forces that hold polar molecules together. In other words, the greater strength of dipole-dipole IFAs over dispersion IFAs. And let's use as a comparison two organic molecules, formaldehyde and ethane. And notice these molecules were chosen, first of all, with respect to molar masses. Their molar masses are almost the same. And secondly, with respect to polarity differences. Formaldehyde is a polar molecule. Looking at its Lewis dot structure, it should be clear when we bring that information about polarity back into our heads that the carbon-oxygen bond is a polar covalent bond. Therefore, the oxygen will be partially negative as the more electronegative atom, center of partial negative on the oxygen, and the center of partial positive on the opposite end of the molecule where the carbon and hydrogen atoms are. So formaldehyde, a polar molecule, it has polar covalent bonds and it is not symmetrical. Ethane, on the other hand, looking at the structure, I immediately see the symmetry of the molecule. So soon as we see that it's a symmetrical molecule, we know that it is a non-polar molecule. But I also recognize that, of course, carbon-carbon bonds aren't polar covalent bonds, nor are carbon-hydrogen bonds appreciably polar in nature. I would consider them to fall in the non-polar covalent bond range. So non-polar covalent bond, symmetrical shape, ethane is a non-polar molecule. So let's take a look at the differences in the boiling points of these two molecules. Formaldehyde has a boiling point of negative 19 degrees Celsius, whereas ethane has a boiling point of negative 88 degrees Celsius. So that's about a 70 degrees Celsius temperature shift or difference between these two molecules. Ethane, as a nonpolar molecule, would have dispersion IFAs as its primary intermolecular force of attraction. Formaldehyde, as a polar molecule, would have dipole-dipole IFAs as its strongest or primary intermolecular force of attraction. And because dipole-dipole IFAs are stronger in nature than dispersion, we would expect that formaldehyde has the higher boiling point in comparison to ethane, and it does, markedly so. Negative 19 degrees Celsius compared to a negative 88 degrees Celsius for the ethane molecule.